Hello, pre-calculus. Um, so I'm going to go over chapter 8, section 2, and these are notes I start. These are notes I started in class, but I'm going to just start over from the beginning and go through the entire set of notes. There's a work packet that goes with these notes that should be posted on Google Classroom. That work packet, the first 2 pages, are note outlines if you want to follow that. Don't have to follow that. Those 2 pages will not be graded, but the rest of the packet will be graded. And also, I have 3 windows open here. I have the notes, a website, and the graphing calculator over here, so I might click through. There's a gap here between the calculator and the notes because I want to be able to click through to each of those. So I'm going to start at the top of these notes, and what we're going to do is we're going to draw the graph, graph the function, sine function. And we're going to do this by plotting some specific points that are nice to graph, and then just going and then just making the curve from there. So some nice points for sine. First of all, you want to make sure you're in radian, which I am. If I put 0 in to sine, I'm going to get 0 out. So that point 0, 0 is an easy point to plot. In fact, you can see that. I can just show this here. That I plotted the point 0, 0 here. So when we're plotting this, by the way, we're gonna make the y-axis from -1 to 1, and we're gonna make the x-axis the radian measurements, and that's gonna go from 0 to 2 pi. So this is, remember, 0 to 2 pi is 1 cycle. This actually will repeat over and over again, this cycle right here that you're seeing. But we're looking at 1 because of coterminal, but we're looking at just one cycle through the whole circle. So 0, 0 is a significant point. The next significant point that is easy to graph is pi over 2. If you put pi over 2 into sine, you get 1 out. So when x is pi over 2, sine will be 1. When x is pi, sine will be back to 0. And when x is, well, there's 2 more actually. When x is 3 pi over 2, we get -1. That's this point down here. And the last one that we have in this graph is 2 pi. When you put 2 pi into sine, you get 0 out. Okay, so now what's going to happen is there's actually another one that we could plot, and I missed it a little. I missed it a little bit here. This graph would also, the only other points that are easy would be this point here. So this is pi over 6. If you put pi over 6 in, you get 1/2 out. And so that would be one point that my graph kind of missed it. It would repeat here. You get 1/2 out here as well. You get -1/2 out here and -1/2 out here. Those are the only other points that are actually pretty convenient to graph. Most of the other all of the other points actually will be irrational numbers. Well, actually not. That's not true, because obviously this graph goes through 1/4 and it goes through 3/4, but it's not an easy angle matched up with an easy ratio that comes out of the trig function. So these are the graphs that have easy in, easy out, essentially. Nice number going in, nice number coming out. All the other graphs, if you put a nice number in, then you're going to get a random, not random, but a decimal out that's messy. If you put, sometimes those, we do know some of those, like √2/2. If you put one of them that we know is sine of pi over 4. Oh, what did I do? Okay, let me start over here. Sine second pi. I missed my second. Not 2. I want to do 4. We get this messy decimal. Well, we know that that is √2/2. So they will, when I say a messy decimal, there are exact ways of writing it, but it would be using a radical, essentially. So so that would be right here, and this value right about here. But these are convenient. These are convenient ones to graph if we're just doing a quick sketch of this graph. This graph is going to have a somewhat parabolic shape, but not exactly, because it's not going to just go down forever. It's going to be almost an exact straight line as it comes out of 0. And then it's going to curve like a parabola, and then it's going to go back to almost a straight line, and then reverse the curve like a parabola this way. And it's going to actually repeat this in both directions. And this is the graph of sine, which I should have put that somewhere, shouldn't have I? Let me just, graph of sine, let me just add that right here, if that's okay. Just take a second. Oops. Gotta fix one issue that is, there we go. If we were to try and graph this on a graphing calculator, we could do that. So if I go into y equals, I'm going to put sine of x, variable button. Now, if I just hit zoom 6, the standard zoom, which I've been using this calculator, so I don't know if it's a standard form, so I'm going to do zoom 6 to make it standard. This is what you get. The function y equals sine only goes up to 1, right? And it only goes down to -1. And then it's going 2 pi would be here somewhere, right? Well, this actually works out pretty well in this case because you can see it, but it's not the best graph because it's kind of small, and some trig functions won't work at all because it'll be so small that you can't really tell what's going on or to go off the graph. We have in the zoom button where I did zoom 6, which was the standard window that I think I've told you about. Like if you want to get a -10 to 10, -10 to 10 graph, you could do zoom 6 to reset your graph if you change it all. Right below that is a zoom trig. This will give a standard window for trigonometry. And what it'll do is, let me just graph it because I'm not entirely sure, but it won't go all the way up to 10. It won't go down all the way to -1. It might go to 3 or something up, or maybe it just goes to 1. And then what it'll do is go to -2 pi to the left and positive 2 pi to the right. So it looks like it's going up to 1, 2, 3, 4 up and 4 down. But you can see it goes 0 to 2 pi and 0 to -2 pi. So this is a better window in general for trig functions. If I go into window, I can see what it did, -2 pi, 2 pi. It changes the scale to this right here, 1.57 I recognize as pi over 2. So that when you look at this graph, this mark right here is pi over 2. This would be pi. This would be 3 pi over 2, and this would be 2 pi. And we have, and thus, in our graph over here, we're not using the left side, we're just doing the right side. We're just starting here and ending here. So that's how you graph this. One thing I did not mention that I do want to mention is you'll notice that on your paper, you're not given the 1 to -1. You choose what you want the y to go to. Since the sine function never goes above 1 or below -1, I chose to make 1 the top and -1 the bottom. But that is a choice you'll make. You cannot change the scale because, and you can see that this is fixed. You cannot change the x scale. It has to go from 0 to from 0 to 2 pi. That's not a choice, but the y scale is your choice. But you do need to label what you chose. So like I chose this to be 1. Now if you only wanted to go up to here and call this 1 and call this 2, this graph would only come up to here, then it'd go down, then it'd come down to here. But you need to label that. Make sure you label your y. This website that I showed in class is a way of, let me just turn off these other two, of also seeing this. And remember, this right here is the circle, the unit circle that we use to get the values of sine. This unit circle is on a different coordinate plane than the trig function. So this coordinate plane is a normal x and normal y. But this coordinate plane that we're graphing on, our y is now the output of the trig function, and our x is the input of the trig function. This is in degrees, but it's the same angle input. And as I change the angle measure on the normal coordinate plane, I'm moving things around rather than, as I increase this, remember sine is defined as the y value over the radius. Okay, so as this angle measure changes, that angle measure is the input on this coordinate plane. A different set of order. This is a different coordinate plane. So that angle measure is is the x values in this coordinate plane. So it's going to go from 0 to 360, okay? And the output that sine gives us is going to be the y value on this plane, this coordinate plane. So you can see that as the angle value increases, the graph goes to 1. But then when it hits 90, it goes from 1 back to 0. And that's because the triangle on the normal coordinate plane that gives us these outputs, the y value goes from 0 to 1, and then goes back down to 0. Once the angle measure goes beyond 90, right here's 90, it stops at 1, that's the height. And then it starts going back down, and then the y value is 0. Okay, so here you can see, and you can use this or the graphing calculator to see the parabolic, well, the trigonometric graphing shape beyond the fixed points that we are given. See, we're plotting these few points, but I don't want you to think that it's like a straight line B shot here and then like a triangle shot down here. I want you to get this curve down that's happening without obviously graphing every single point, because it would be tedious. You just need to graph those very important points and then mimic the curve. When we're at, by the way, going back to this, it switches back, so it goes 0 to 1 because the y values go from 0 to 1, and then they go from 1 to 0. And then they're going to go to -1. They're going to go from 0 to -1. After 180 degrees, I mean, when it gets to 270, it'll be at -1. And that's because the radius now is -1. Sorry, the y value is -1. The radius is still 1. No, radius is always 1. The output of the trig function is now -1. And then we're going to go the last leg of the first cycle of this coordinate plane, and we go from -1 back to 0. And then we just keep repeating that. This little activity doesn't allow me to go on, but it would just keep repeating that and starting over. So while this ordered pair just loops, right, goes loop, 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 this one continues to grow in the x-axis forever, and also in both directions. Okay, so hopefully you're getting an idea of what the sine graph looks like from this. Now we're going to do the cosine graph, and we're going to go through the same process with the cosine graph. Before I show the graph of cosine, let me clear this. Let's put some values in. Cosine of 0, when you put cosine in, or 0 into cosine, you might remember from the table, you get 1 out. Actually, let me just pull this up. You're going to get 1 out when you put cosine in, or sorry, when you put 0 into cosine. Cosine of second pi over 2. You put that in, you get 0 out. So this function is going from 1 down to 0. And then cosine of pi, you're going to get, I'm just showing you that this works, and these values up here are good. You're going to get, I should put the function here too. You're going to get, as you can see, -1. Whoa, what did I just do? Y equals cosine x. It's the graph that we're functioning. I should just label that there somewhere, so that's clear. There we go. And then cosine of 3 pi over 2. We get 0 again. And then cosine of 2 pi, we get 1. So those are our important points. Again, this will go through 1/2 at, in this case, 3 pi here. I hit that a little better in this graph. Here, here, and here. It's these 5 points that I'm mainly interested. I want you to make sure you plot these 5 points again. I'm choosing the y-axis to be 1 to -1. So the top up here is 1, the bottom down here is -1. As I go through this process, you get to choose that, but you have to label what you choose. Go over here. My trig function window is already set up. I'm just going to overwrite sine, and you can see here that matches. Of course, we're going from here to here, and again, this repeats. You do want to make sure that you act at the end of this like it's going to repeat. Don't come up here at a straight point like a pyramid, or a triangle, I should say. Come up here and flatten out like you're going to come back down on the other side. You're going to come back down the other side on this one too. So this is the graph of cosine. So let's look at cosine over here. See the outline. If you go through the process, cosine is defined as x over the radius. So the x value starts at 1 because our ordered pair here is 1, comma 0, 0. And as you grow the angle, you get closer and closer. It forces it closer and closer to x being 0, which would be when it lands on the y-axis. And then it x's in the negative. And that's what's happening here. That this right here is going from 1 to 0 at the end of the first quadrant. So this region right here is the first quadrant. This region right here is the second quadrant. At the end of the first quadrant, it's now negative because the x values are negative. The furthest it gets away from the origin, the x value is going to be when it hits -1. And then it's going to work its way back. It's going to be 0, and then it's going to be positive again. And then I'll just keep on doing that repeat, just like sine. So why is this so important? Because we're going to actually do some transformations on these two graphs. We're not going to just be graphing those. We're going to be graphing transformations on these, and we're going to do that in a minute. First, let's define two things. The period of a function is how often it repeats. For the default, y equals sine x and the y equals cosine, so the parent graphs, that's what we call parent graphs of sine and cosine, the period is 2 pi. But when we do transformations, that period might change. The amplitude, on the other hand, unlike the other functions that we did transformations on, we didn't have period or amplitude. But one thing that's unique about sine and cosine is it has an amplitude, and that is the height the function reaches and the depth it reaches, essentially. So how high it goes and how low it goes is an amplitude. That amplitude is determined by the distance it gets from 0. So it's going to be 1 when it reaches 1 and goes down to -1. It's going to be 2 if it goes up to 2 and goes down to -2. So it's not going to be it's not going to be 2. How do I say this? It's not going to be 2 because 2 and -1, or because 2 is the distance from 1 to -1. It's going to be the distance it is from 0 up and 0 down. Okay, so by default for sine and cosine, the amplitude is 1. Okay, how do you find the amplitude and period of transformations on trig functions? Well, we're going to look at this. This is kind of like a quadratic formula. You know, remember that ax squared plus bx plus c? Well, we have here y equals a sine bx. So integers will be placed in the a and b spot for both of these. And what the a value does is it changes the amplitude. Whatever this value is, and you can see on the original function that it's going to be, if there's nothing there, then a 1 is there. So whatever that a value is what the amplitude is. So if there's a 2 in front of the sign, then the amplitude is 2. And if it's a -2, the amplitude is still 2 because we take the absolute value of whatever that value is in front of the trig function. Same with cosine. Whatever the number is in front will determine the amplitude. Oh, sorry. Bumped the mic there. The period is determined by the number in front of the x inside the trig function. And when there's nothing there, it's 1. So the period by default, if b is 1, 2 pi over 1 is 2 pi. So the period by default is 2 pi. If there's a 2 in here, then 2 pi over 2 would be 1. So you'd have a period of 1 pi if there was a 2 inside one of these trig functions. If a 1/2 was in here, I didn't do this for the amplitude, but it could be a 1/2 out in front. If a 1/2 is in here, 2 pi over 1/2 is actually 4 pi. So that actually will stretch the period out. And so what does that mean? If the period is 2 pi, it repeats from 0 to 2 pi. But if it is 4 pi, because the 1/2 was in there, it's going to stretch out this cosine function, and everything that's plotted is going to be twice as far away from the origin as it is. So this stays where it is, this 0. But this point here would actually be here. And this point here would be doubled and would be here. And you'd only see half of the period on this graph because we're fixed between 0 and 2 pi. So it would do something like my cursor's doing right here, is what it would do. Hopefully that makes sense. If it was pi, if the period is pi, then everything is cut in half. So this stays where it's at. This gets plotted here. This gets plotted here. This gets plotted here. Moves half in, so just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 if you have to count. Then go 1, 2, 3, 4, 5. So it's going to move in to wherever that was. I lost my count now, my place. But what should happen is you should end up doubling the number of if the period is pi, then you're going to see 2 cycles of this function in this window that we're given. I'm hoping that makes sense, but we're going to do an example here. So hopefully, if that didn't make sense as my description, hopefully the example helps. So 3 sine 2x. The amplitude will be 3 because 3 is the a value, and the absolute value of 3 is 3. And the period will be pi, so we're going to get a chance to see this. So what does that mean? Well, I'm just going to have to show you the graph because, sorry, it's a little crooked. It's just when I scanned it, it didn't come in straight. I don't think I can rotate it in here very easily. I should have done that in another program. So what we're going to do is, with an amplitude of 3, that means our height, the highest point this function reaches is now 3, and it goes down to -3. We're dealing with the function sine. Keep that in mind. So that started at 0, went to 1. This is my original, this dashed line here is my original function, by the way. And the reason it's so shallow is I had to change the scale to meet the amplitude. So I'm changing these dashes. Instead of going all the way up to 1 here, I'm going, the highest point will be this. It's going to be 3. So this is my 1. So my original function went 0 for sine. 0, 1, 0, -1, 0. That's the dashed line. That's the parent function. And 1 being here and -1 being here. So now what's happening is my amplitude is that's going to get stretched to 3. So this is going to go up to 3, and this is going to go down to -3. It's still going to be 0, 0, and 0, but those 2 points get stretched. That's how the amplitude affects it. The period part affects it by going through that entire cycle, though, the 0, 1, 0, -1, 0, from 0 to pi instead of 0 to 2 pi. So then that's what you see as the final product. This right here, which is 3 units away, gets put into this 1.5, like halfway between these two. Okay, and it goes from, so it's going from, so my normal 1 value is not only moved up to 3, but halved the distance. Okay, this right here, this value here at 6 will be 3. Well, that's what happened. This should be at 9. This will get moved to 1.5 or 4.5. Sorry, 4.5. I counted 10 accidentally. The other one. That's why I got confused. And this one here, which was at 12, will be at 6. See how it goes through the whole cycle. 0, 1, 0, -1, 0, and finishes at pi. One whole cycle from 0 to pi. Well, because our window goes to 2 pi, we have to repeat that then. Do it as many times as you can in the window that are given. You have the ability to adjust the y-axis value, and you want to do that. You want to don't make this -1 and this 1 and then have it go off the graph. Adjust the y values, but you don't have a choice of the x values. So you have to go through 2 cycles when the period is shorter. And if the period is longer than 0 to 2 pi, you put whatever part that you can. Okay, so let's do an example where it's longer. Here we have an example where the amplitude is 1/2 and the period will be 4 pi. So it's only going to show, we're only going to be able to show half the period, and this is now cosine, so that's an important part too. Cosine originally went 1, 0, -1, 0, 1. Okay, so you can see my original here, and now I'm going to go back to having it go from 1 to -1 because I'm going to zoom in on the y because I'm going to try to graph 1/2, and if I did this, the 1/2, if I did this window, the 1/2 would be here. It'd be really, really tiny. We'd have all this empty space that we don't need to have. So I'm doing 1 to -1. That's where I was at. So this is now 1/2 here. So instead of going all the way up to 1 and all the way down to -1, we're going to go up to 1/2 and down to -1/2. And then in addition to that, it's going to be stretched. So where it was 0, it's going to be twice as far away from the x-axis. Where it was -1, which will be now -1/2, is going to be twice as far away from the x-axis. So you're only going to go through half of the cycle, and then we're going to be done because we ran out of space. So it's going to start at 1/2, go to 0, and then go to -1/2, and we're done. Because this period is stretched, and we don't have the room for all that. You can double check these if you want, no problem, on your graphing calculator. So I didn't do this with the first one, but always put fractions in parentheses for safe. That make sure you do it right. So I'm putting the 1/2 in parentheses. Order of operations going on there. So I just put 1/2 cosine of 1/2 x in, and I have the right window, so I think I can just graph this. And again, we're starting right here. And you can see how it's what we have is doing that. Now the window is still going to 4 and -4 up here, which you can adjust if you want to. But you can see how it's only going through one cycle. I didn't do that for the sine one, but you get the idea. You can look at it on here. Okay, so I think that's it. Yep, that's it. So then what I have is 2 work packets. One work packet is graphing of these things, and the second work packet is more practice with the previous problems that we were doing, solving trig equations. So that's all I have for this lesson. Thank you and good day.